just focus on two of my works of last year. It's on model merging. I think it's a very interesting topic, and I hope you will agree at the end of this talk. Let's see, we are in the foundation model era. These models are typically trained once with a lot of data and a lot of compute. And they are then used by the community to fine-tune their own experts, so to specialize in, for example, mathematics. As such, these foundation models can be seen as a universal starting point for experts to be trained. So building these experts is also still a hard task. It requires data, it requires compute, and it requires expertise. Happily, people in the community are making these models available on websites like Hugging Face, and you can freely download them and use them for your purpose. But then the question comes, maybe I want to combine the capabilities of multiple of these experts in a single model, and how can I do that? Is that possible? So that's where model merging comes in. It aims to combine these experts in a single model. It aims to do so without having access to the original training data. And it requires no additional fine-tuning typically. This field was started a couple of years ago with a paper, Model Soups. In this paper, people were just working on a single task, so a single expert, you could say. But I trained 100 experts on the same task with different hyperparameters. They changed the batch size, the optimizer, etc. And these models are printed here in green dots in this graph, and I put it out on the horizontal axis against the target dataset, so the dataset which they are trained on, and on the vertical axis on out-of-distribution performance. And what you can see as a reference, there is a gray dot, which is the original foundation model. So all the models which they trained, they get better in the target tasks. They are more on the right. Some are a little bit better on out-of-distribution. Most are a little bit worse, so there is some forgetting going on. What you would typically do is maybe pick the model with the best hyperparameters. So you would take one in the right top corner. But what these people found was that actually if you took all the models and you just took the average, you get a blue dot. And that does very good on the target distribution, and it's the best model on the out-of-distribution. So that's a very simple operation, just averaging the weights of all these models into a single model, and you get a very good model. So the community was a bit amazed about these results. People picked up later in iClear 2023 and went one step further. Instead of training on the same task, they trained experts on different tasks. And I defined the concept of a task vector, which is a very simple equation. On the top, you take your expert model parameters and you subtract the foundation model parameters, and you get your task vector. And then if you do merging according to the equation at the bottom, where you just sum all the task vectors, you multiply them with a single scalar and add this to your foundation model, you actually are accumulating the capabilities of these various experts into a single model. So that's what you see here in the graph. They're adding on the horizontal axis more experts, and on the vertical axis you see that performance on all of these experts tasks averaged is going up. So this is quite surprising. A very simple equation to join without having any training data, various models into a single model. And here these are vision tasks. So it's 8 different vision tasks. So just for people who maybe think it's not so amazing, so why do we thought this, for most people, this came as a surprise? Because in our heads we have this idea that to optimize neural networks, we have a loss landscape, and it looks a little bit like the one on the left. And you have these islands where the solutions are found. And if you would average these these islands, you would get somewhere in the blue area on a ridge, and it would be very bad. So you are in a high loss situation. Some people were doing research to what I call mode connectivity. So they see, is there some way that these different minima in the loss landscape are connected? And on the right, you see some sort of mode. Often this was found, actually, there is some sort of mode connectivity. And what we now found is that in case of foundation models, there is actually often linear mode connectivity, and that means that a direct line between the different minimums is still going to a low loss landscape. And that allows us to do simple equations like the one in the bottom, where you just average various models. So a very simple way to accumulate capabilities by a simple operation. So here we started looking into this research field, and here are the 8 different vision tasks. At the end is the average performance. In blue you see the zero shot, in green you see the expert performance, and in red you see the model merging performance of task arithmetic. And you see it's getting pretty close. It's not as good as green, so keeping all the experts is still better, but model merging gives you everything in a single model. And you see what we've noticed was that for some data set it works very well, for MNIST and Euroset, for others not so good, for example for cars and DTD, which is a texture data set. So why we wanted to understand this better. And what we did is we looked at this metric, which is called the subspace alignment ratio. And it's a very simple metric. It looks at the model merged update, and it looks at the principal factors of this update, and it looks how they overlap with each of the experts. So you look at the overlap between your model merged update and each of the experts. And if you do this, and you plot this against the performance gain on the vertical axis, you get something like this. And what we saw, so more alignment on the horizontal axis leads to more performance gain. So here in the bottom of the screen we are at zero shot performance. On the top you are as good as your expert. And what we want to be is we want to be in this right corner again, where we, or at least in the top, we want to be as good as the expert. So we saw this clear correlation, and we thought, so let's look deeper into this. We also noticed that some data sets maybe are overrepresented. So there is SVHN and there is MNIST, which are doing similar things. There are 2 satellite data sets, and these are also the ones which get the best results. So maybe there is some overrepresentation, and the data sets which are kind of on themselves in this set of data sets, like cars, they don't get a big boost in the final merged model. So we looked at the singular values of the merged model update, and indeed, what you always see, you see some of the directions are dominant and others are less dominant. And we thought, okay, let's just get rid of these dominant directions. And we did something very simple. We just whitened this spectra, and we replaced it with an average energy in all directions. So equal importance of all the directions. This is a very simple operation. The final algorithm is 5 lines. So you sum all your task factors. You take an SVD, which gives you the U, the sigma, and the V matrices. You kind of throw away the sigma matrix almost. You just reconstruct the matrix with your U and V matrices. You still multiply it with the average energy. It's a scalar. And that is your update. So a very simple operation. And if we now look again at the alignment, we are looking at what is called isotropic model merging in the triangles. We see that the alignment went up. They all now above 0.9. And with the alignment, also the performance went up a lot. So this simple operation, now you get very close to expert performance on merging 8 various tasks. And it looks like this if you look at all the, if you compare it again with task arithmetic in red. So you see that the yellow method is now very close to the green expert method, but then in a single model. Now you can still go one step further. So if you look at the spectra, there are often some directions which are least important. We also looked at the performance of these various experts as a function of how many of these directions you take into account. And if you do that, you see that you can throw away the upper part or the least important directions. And that's what we did. And we filled these least important directions with task-specific subspaces. So it's a very simple addition to this method. And this gives us an additional performance boost. So here is comparisons on 8, 14 and 20 vision tasks with 3 different models. On the right you see the large VITL, and the last you see, for example, for 20 tasks. If you do 0 shots, you get 65. If you train your experts and you keep them all, you go up to 95. And now if you use our model merging method, which was state of the art last year, presented at ICML, you get up to 90. So the gap is getting smaller. We also did this for language models. Here we merged 8 very different language models. And again, you see a big jump from task arithmetic, which gets 64, for example, for 8 tasks, and we jump up to 75 here. So yeah, all these methods are merging methods on full weight space, so they consider full learning of the weight space. Typically what we do nowadays is actually sparse updates. We do low rank updates, and we make LoRAs available. And a simple thing to do is you go to the full weight space and then do the merging, but of course this is not efficient. So last year in a NURBS paper we looked into how to make this more efficient. I will say just 2 minutes something on this. You can naively, of course, do also the merging of the A and the B matrices. You can do task arithmetic on that, for example, but that fails badly. At the time, there was only a single paper of iClear last year which was doing LoRA merging. But these people also still needed to go to the full parameter space. Then they went back with the SVD. But this made the algorithm, in our opinion, still a bit inefficient. So we were thinking, can we not exploit this low rank space where we are in anyways? Oh, sorry. So that gave us our method, which is core space merging. It's actually mathematically very simple. What we did is we concatenated the A matrices and we concatenated the B matrices. You do this throughout the whole model. And you do an SVD on these concatenated matrices. And then you take the V matrix from the decomposition of the A's and the U matrix from the decomposition of the B's. And if you take these 2 matrices, they together define a subspace, which we call the core space. And in the paper, we show that there you can do operations without any loss of information for any of the experts. And this is still a low rank space. So you still have the computational efficiency of the low rank there. If you look quickly at the results, then in green is our method. This is on the horizontal axis the amount of compute you need, and on the vertical axis the accuracy. So our methods are way faster, so up to 600 times faster than the existing NOTS merging method, and still slightly better, so 1.5% gain with respect to other methods, by doing it in this compact core space. So that brings me already to the conclusions of this talk. I think model merging is a very efficient or interesting research topic. You can efficiently combine independently trained experts with very little compute. ISO merging shows the importance of looking at subspace alignment, and if you manage to improve that, you can get a much better merging algorithm. And in the end, we show how to do low-rank updates efficiently. This work was done by 2 visiting students at the CVC, Danielle and Aniello. Danielle from the IDES Institute in Warsaw and Aniello from Modena University. And that's it. Thank you for your attention.